So before we go to the risk management in analytical chemistry, we go to the introduction to risk management concepts. There are two definitions that we need to know first. The first one is risk and the second one is hazard. While both of these words may seem similar, there are differences. The first one is risk. It is defined as exposure to danger or the likelihood of an unpleasant event occurring, while hazard is a biological, chemical, or physical agent that could cause harmful effects to health. So basically, hazard is the danger itself, while risk is the likelihood of someone to be exposed to the danger. So we see here the difference is hazards are the source of potential harm, while risk is the likelihood and severity of those hazards causing harm. We also need to understand the core process of risk management. It involves risk identification, hazard identification, risk assessment, and decision making based on risk analysis to address threats and support decision making. For the risk assessment, it is a critical step in the broader risk management process, evaluating the probability and severity of risk, considering management alternatives. The last step of the process would be risk management strategies. Decisions are made based on the findings of the risk assessments. So it leads to strategies like avoiding, reducing, transferring, or accepting risks, along with developing contingency plan. There is also risk communication that is involved in every step. It plays a key role by ensuring transparency and clarity between risk assessors and the managers.
I will be comparing risk assessment methodologies in analytical laboratories with a focus on global practices and how these strategies are adapted for Malaysian context. This is a critical topic because quality assurance ensures the reliability of the results, whether in research labs or industrial settings. Globally, the labs follow internationally recognized standards like ISO 15189 and ISO 31000. These two frameworks emphasize structured steps, which is risk planning, identification, analysis, response, and monitoring. Tools like Ishikawa diagrams, failure modes and effects analysis (FMEA), and fault tree analysis (FTA) are commonly used to identify and evaluate the risk. For example, the journal highlighted that Romanian labs prioritize using these methods to create risk matrices and ensure preventative actions are in place. The focus is also on creating a risk-aware culture through systematic training and documentation. Residual risk, those remaining after the interventions, are continuously monitored and addressed through quality control plans (QCP). In Malaysia, the approach is similar, but it tailored to local regulations and industrial needs. For example, the labs here follow the updated ISO 15189, aligned with international standards but specifically addressing Malaysians' healthcare and industrial needs. The Medical Device Act 2012, Act 737, and Occupational Safety and Health Act 1994, OSHA, further guide labs in ensuring both safety and quality. For instance, Malaysian labs integrate risk-based thinking into their quality management system (QMS), focusing on tools like FMEA to address localized risks. A key difference is that compliance with Malaysian regulatory frameworks like Standard Malaysia's accreditation ensure laboratories align with both global best practices and national safety requirements. This dual focus ensures that results are not only accurate but also legally and ethically sound. Another advantage in Malaysia is the strong emphasis on training. For example, MS ISO 15189 requires continuous skill development to meet accreditation standards. This ensures both new graduates and seasoned professionals understand how to effectively manage risks.
Now, we move to the next subtopic, which is the application of risk management in analytical laboratories. The first crucial aspect of risk management is risk identification and assessment, where laboratories pinpoint potential hazard related to equipment, sample, region, and personal practice. Tools like FMEA and HERA are used to evaluate the probability and severity of these risks, allowing laboratories to prioritize them effectively. Second, another critical application is error reduction, which enhances the accuracy and consistency of laboratory results. Guidelines such as CLSI EP18A2 provide detailed guidance on mitigating risks related to measurement uncertainty. For instance, implementing automated system to handle sample preparation, minimize human error, and ensure reproducibility, reducing variability and test outcomes. Furthermore, regular staff training ensure that personnel are well-versed in standard operating procedure. Third, quality control and assurance are other areas in which risk management play a vital role. A risk-based approach to QC, as outlined, involves tailoring QC plans to maintain high standards in their testing and reporting process. For instance, in laboratory dealing with clinical diagnostics, periodic calibration of equipment like spectrophotometers ensure that deviations are detected early. So, SPC, which is statistical process control, laboratories can monitor trend and take corrective action before error manifests in final result. Next is safety management, which focuses on the proper handling of hazardous material. For instance, laboratories often adopt globally harmonized system, which is GHS labels to communicate hazard effectively. Additionally, investment in engineering controls such as fume hood and biosafety cabinet mitigate exposure to harmful substance. Regular safety drills and the use of appropriate PPE further ensure preparedness for emergencies. Another important application is process optimization, where risk-based decision-making help laboratories identify inefficiency and streamline workflow. For example, laboratories using IoT-enabled predictive maintenance system can monitor equipment performance in real time. And the last one is risk management facilities, which is indicate prevention and mitigation by proactively addressing potential hazard and implementing comprehensive emergency response plans, such as spill containment protocol for hazardous chemical. For example, readily available absorbent kits near high-risk area allow for immediate containment, preventing the spread of fuels. Fire safety measures such as installing fire suppressing system and conducting evacuation drills will further enhance the preparedness.
Next, case studies demonstrating risk management success. Based on the case study entitled Approaching Risk Management in Medical Laboratories, I will focus on three key areas: the pre-analytical phase, risk-based thinking in the analytical phase, and near-miss event reporting. First, the pre-analytical phase involves tasks like patient identification, specimen collection, and transportation. This phase is prone to errors such as mislabeled samples or improper handling. To address these risks, one laboratory used failure modes and effects analysis, or FMEA. The team evaluates the severity and detectability of potential error. For example, they implement strict specimen labeling guidelines, improve transport monitoring system, and train staff in patient identification protocols.
This action significantly reduce error and ensure reliable test result. Second, laboratories integrate risk-based thinking into their quality management system following ISO 15189-2012 requirements. Tools like the Ishikawa diagram and Pareto analysis help identify risks in the analytical phase, such as equipment malfunctions or reagent calibration issues. By addressing these risks, laboratories implement regular equipment maintenance, continuous calibration check, and strict quality control process. This approach minimizes analytical error, improve test reliability, and ensure accurate diagnostic. Last but not least, laboratories manage near-miss events, which errors that are detected before they affect patient care. Using fault-tree analysis, laboratories identify the root cause of this near-miss and take corrective measure. Staff are encouraged to report these incidents rather than overlook them, supported by a clear reporting process and targeted training. This strategy builds a culture of accountability and learning, leading to fewer critical incidents and better patient safety. By focusing on pre-analytical risk, analytical process, and near-miss events, they ensure accurate results, reliable performance, and ultimately the safety of patients.
So for the last part is future consideration for risk management in laboratories. I will explain about 3 considerations. So the first consideration is greater integration of digital tools. So in the case study mentioned earlier, the laboratories are using advanced tools such as failure mode and effect analysis (FMEA) and also fault tree analysis (FTA) to identify and analyze risks. So this now being supported by even better technologies such as using laboratory information management system (LIMS). So this system can help to manage data efficiently and send alert for many issues, reducing errors. So the second one is Internet of Things (IoT). The IoT device can monitor things like temperature and humidity to keep samples safe and in the right condition. So by using their automation, this technology can help to reduce human error, speed up workflow, and improve accuracy during the lab process. So the second consideration is sustainability in risk management. In ISO 15189-2012, this encouraged labs to reduce risk management in their quality system, and this can be expanded to include the sustainability. For example, laboratories can manage waste, energy, and chemical more responsibility, follow green chemistry principle and sustainable sourcing practice, and also use approach like reclaiming solvent and recycling material to reduce their environmental impact. So there is a study show that using technology like digital twin can cut out down the waste and support the sustainable practices. So last but not least, the third consideration is predict, review, and continuous involvement. So regular audit and risk assessment can help laboratory identify problems and update strategies for the new challenges. So laboratories also can collaborate with university and also tech company to bring in artificial intelligence (AI) to predict risk and analyze their impact, and also sensor to provide a real-time quality control. So by partnering with this lab, can improve the process and stay proactive in managing risk.